Okay, so please, we're looking forward to your third lecture. And just to remind that the next lecture will be next Tuesday on the 17th. Okay, thank you, Jean-Luc.
Thank you very much. Yeah, so last time we discussed how we could go from curves on the torus to curves on the disk by using this quotient space construction, using this map called that we call iota, which has this technical name called the hyperelliptic involution. It can be applied to other surfaces. I might talk about that later. But the point is this map basically rotates the torus about its center. That's one way of seeing it. And you identify points on the torus that are related by this map iota. And I tried to convince you last time that this led to a surface which is actually a sphere with 4 punctures. Then we blow up one of these punctures to make the outer boundary of a disk. And we blow up usually the origin because that's a fixed puncture by all linear maps. And loops, so closed curves on the disk, on the torus, get projected down onto the disk. So for instance, this closed curve, which passes between punctures 1 and 2 and 0 and 3, looks like this, at least topologically. There is an explicit construction of this map, by the way. It's called a Weierstrass map. So you can actually build this map, in practice. And these are called the Weierstrass points. So this is like the general area of kind of elliptic, the Weierstrass elliptic points, things like that. So, but in practice, we don't actually construct this map explicitly. We just kind of, topologically, we're happy to understand what it does topologically. And so remember that we had these 2 parabolic elements, T1 and T2. I told you they would play an important role. And this is where they start to really shine. Because for instance, if I apply T1 to this curve, then it transforms this loop to another loop. And it turns out it maps it to something like this. So it has the effect of interchanging the puncture 1 and 2 clockwise. And similarly, puncture T2 will have the effect of interchanging punctures 2 and 3 clockwise. They're both clockwise. The minus sign ensures that that's the case. That's just a small technicality about orientation. And I told you that any element of the mapping class group of the torus could be generated by taking products of these elementary operations called Dane twists. So on the torus, they represent kind of twisting a curve about one of the directions of the torus, but on the disk, they correspond to this operation of an interchange of 2 rods by pi. In fact, they're kind of a Dane half twist on the disk because of the double covering projection. Okay. So this construction now suggests, what should we do when we have more punctures available to us? What if we have a stirring device involving more rods than just 3? Right? And this is, where we launch into our next big topic, and that is the topic of braids. So those of you who know what I work on might have wondered why we haven't said anything about braids so far. So how do braids come in? Well, the idea is that if I have a disk with 4 distinguished points with 4 punctures, let's say they're rods of my Taffy puller or rods of a stirring device, or even just orbits of a dynamical system, then I can draw a kind of space-time diagram of the motion of these points. So here I'm just drawing some arbitrary motion of the points, and here I'm plotting T vertically. So you're lifting the motion of these points to a space-time diagram. But I'm demanding that the points return to where they started as a set. In other words, maybe a point can swap position, like this one starts at position 2 and ends up at position 1. So maybe they can be permuted, but they go back to exactly the same points that they started. And so this is exactly what is called mathematically a braid. A braid, I'm going to do, so first we define a geometric braid. A geometric braid is simply a collection of strands in R2 cross I, where I is the interval, so time, right? Such that for one thing, the strands are not allowed to cross ever, right? So once you decide that the strands are separated, right, they can never touch, then we only define equivalence of braids up to continuous deformations of the braid. So you can never have one strand go through each other. If you ever studied any knot theory, that's exactly the same setting. Another small technicality is that braids don't go back in time like this. So we don't allow strands to kind of double back in time and then continue moving forward. It turns out that that's a very minor limitation in the sense that any braid that does this can be deformed, one that doesn't do this, right, by kind of pulling on it a little bit. In practice, because our actual parameter is time, for us, this is not really a limitation because time marches forward for everyone. So it's not really a limitation to demand that the braids. Okay. So that's a geometric braid. There's a more general definition, which is quite pleasant, which is having to do with the configuration space of points. So in other words, if I give you any space, could be a sphere, could be a torus or something like that, and I put some distinguished points on this, there's a space called the configuration of such space, of such points, which is all possible ways of laying out these points on the surface such that they don't coincide. And the braid group can then be identified as the fundamental group of that configuration space. In other words, remember the fundamental group was the space of loops, where you can think of a braid as a loop, but where this configuration is considered as one point in some sense, right? So these points are moving around, but they count as one point as far as the configuration is concerned, and they return to their initial configuration. There's a special type of braid if all the strands actually return to their initial point-wise rather than as a set, then this is called a pure braid. Otherwise, it's just called a braid. But we won't really need the distinction between pure braids and regular braids very much in this. Okay, right. So the so-called geometric pictures of braids, and again, by the way, we define braid equivalence if two braids can be deformed into each other. I think I already mentioned that. And braids form a group, which we call Bn, the braid group on n punctures. And usually we're going to define this group as being on the disk with n punctures, where n punctures is these n distinguished points that are not allowed to collide. So how is it a group? Well, it has a composition law, which is just to chain braids together naturally. So in other words, because they return to their initial points as a set, right? If I have a braid that does this, I can add another braid that does this, right? And this is where I join them, and the resulting thing is still a valid braid, always. Okay. So composition is defined, and it's pretty obvious that this is associative. There's an identity braid, which corresponds to doing nothing. And finally, there's a way to do the inverse. Okay? So the inverse of the braid corresponds to, if I'm crossing like this, I guess I'll just uncross. And now you can see that I can slide the top string to make the thing isotopic to the identity braid. So I'm just drawing 3 strands as an example. So I can slide this top string here, which is not really entangled with the second string, to give me the identity. Okay. Right. So this is composition, identity, and inverse, and associativity is pretty obvious. And so, ergo, equivalence classes of these curves called braids form a group. Okay. So this is the picture for geometric braids. But then we like to pass to a more convenient representation that we call algebraic braids, where I replace all of this by symbols. And the idea is the following. let's say I start with this braid that I drew here. I'm going to move the strands around in order to standardize the picture a little bit. So I actually drew, unfortunately, a pretty simple braid, right? Almost none of these strands are entangled, except maybe the first two. But let me draw it anyways. What I mean is that we draw this diagram like this. So we smooth out the strands and pull them however we want until we reorganize the braid such that it looks like a sequence of elementary switches of adjacent strings. So any braid can be rewritten by sliding things up and down. So in other words, if I have two switches happening at the same time like this, because they don't share a strand, I can slide one up a little bit. This, in order that there's only one exchange that occurs per cell, if you will. So if you divide the braid into blocks in time, you can always comb the braid a little bit such that only adjacent switches occur and only one adjacent switch occurs per cell. Okay. And so what we do then is we denote these elementary adjacent switchings by some symbols. So if I label this string as 1, 2, 3, and 4, then I will define the operation sigma 1, which is called a generator of the braid group, as the clockwise interchange of strings 1 and 2, where clockwise has to be defined with some arbitrary convention, right? So you either define it clockwise from the top or clockwise from the bottom. It's up to you. Different conventions exist in literature. I usually think of clockwise, when looking at the thing head on, but when you draw the braid like this, it's a bit less ambiguous. It's a bit more ambiguous what you mean by clockwise. And similarly, so the 1 here, when I write sigma 1, it means the exchange of string number 1 with string number 2. And similarly, this second generator here, I would write as sigma 2, because it's the exchange of string number 2 with string number 3. So in general, make a very big picture here. One generator looks like this. So if this is string I, and this is string I plus 1, then this elementary exchange of two strings, I call sigma I. So sigma I is the exchange of the I string with the I plus 1 string. And so clearly I can run from 1 to n minus 1. So there are n minus 1 generators for the braid group Bn. Similarly, if I change the direction of my crossing, that's like, changing an over-under to an under-over, and we write that as inverse. That is the counterclockwise exchange of strings, and so it makes sense to define that as the inverse because it is actually the group inverse. It cancels a sigma I inverse, cancels a sigma. Okay, so we have our generators. The way one writes a group very often, especially such a thing as let's say we want to write B3. The way B3 is written often, it's a group of two generators, right? Because I can only take values 1 and 2. So I would write that this group is generated by sigma 1 and sigma 2. But this is not what's called a free group. So last time we talked about the fundamental group a little bit. I think in the first lecture, we had these generators of the fundamental group, which were just loops. And these loops have the property that they obey no properties other than inverses, etc. So they didn't commute, there was no special relations held. The braid group is not the same. It has intrinsic relations. In fact, the braid group B3 has one such relation, and I'm going to draw it here. A relation is a relationship that is satisfied between the generators, but that is not an inherent property of just being a group. For instance, saying that sigma 1 inverse is equal to the identity E, that is not a relation because it just follows from the fact that sigma 1 is an element of, right? So that doesn't count. But the braid group has one really nice relation, which you can sort of prove almost visually. And that is that, so relations are written this way. We say vertical bar such that sigma 1, sigma 2, sigma 1 is equal to sigma 2, sigma 1, sigma 2. Okay. So why is this true? Well, you can just draw it. It's one of those cases where a proof by picture really accomplishes most of what you want. So this is a sigma 1. I'm writing it as an over in this way. And then this is a sigma 2. And this is another sigma 1. Okay. Very more discrete. Hopefully you can see this. The claim is that this is equal to sigma 2, sigma 1, sigma 2. So let's draw that. So we draw a sigma 2. We draw a sigma 1. And then we draw another sigma 2. Okay. So now you do a proof by staring. And you notice that the top string goes between 1 and 3 above all the other strings. But that's exactly what this string is doing as well. And similarly, this string goes under everything, exactly the same as this string. And then finally, the third string is between the other two strings. So it really is just a half twist of the first and third string around the second string. In fact, in this particular case for B3, it is called the half twist. So clearly this relationship then is correct, at least up to deformations, right? Up to my definitions of the braid group. But what is surprising is that this is the only relation. Right? That requires proof, and I'm not going to do it, but the point is that this is the difficulty, right? Is to say, is there any other relation possibly satisfied? Like it could be that sigma 1 squared times sigma 1 inverse is equal to sigma 1. Maybe that's true, but it turns out it isn't, because any relation you have should be derivable from this one plus the elementary group operation. But it's a difficult problem often to prove that you have the so-called presentation of a group. So again, listing the generators followed by the relations that they hold is called a presentation for a finitely generated group. So B3 is an infinite group because you can take a large number of products of these sigma 1 and sigma 2s, and sigma 1 and sigma 2 never repeat, right? If you take a large power of sigma 1 to the k, that never becomes the identity. It's not cyclic. And so you have an infinite number of elements because you can just keep taking powers of sigma 1 and sigma 2. But sometimes some of those elements will be the same. So for instance, if I have sigma 1 squared, sigma 2, sigma 1, then that's equal to sigma 1, sigma 2 squared, sigma 1. 1, 1, 2, 1, but then I replace the 1, 2, 1 by 2, 1, 2, and I get 1, 2, 1, 2. I wrote wrong. And it's quite a difficult problem to try and eliminate, to simplify a braid by using these relations. In other words, you might have a very long representation of a braid in terms of these symbols. This is called a word when you have a product with generators. And you can ask the question, can I use these relationships to shorten the braid? And it's actually a difficult computational problem to figure out how to apply the relations to make the braid as short as possible. It's an interesting computational problem, how to do that. So there's a whole group of mathematicians that work on these kinds of group word problems. It's a big industry. Okay. Any questions so far?
No, so far it's perfect.
So what about higher groups, right? So what about Bn? Well, Bn will have sigma I, where I being between 1 and n minus 1. And then it turns out it'll just have two types of relation. One of them is that sigma I plus 1, sigma I is equal to sigma I plus 1, sigma I plus 1. So this is just the same relation. This is often called actually the braid relation. And the reason why it's still true when you have more strings is because you could just think of this as being string I plus 1, and string I plus 2. And then what the other strings are doing, meanwhile, is totally irrelevant. So this braid relation is really kind of a local thing between three strings. It's nobody else's business but the three strings under consideration. So these are all true then for I equals 1 all the way to n minus 2, right? Because the relationship involves I plus 1, and I only have n minus 1 generators, this gives me n minus 2 relations. So when n was equal to 3 for B3, then that's one relation. Okay. But that is not it for Bn. There is another type of relation, and that's the commutation relation, which says that sigma I, sigma j is equal to sigma j, sigma I, as long as I minus j is bigger than 1. Absolute value of I minus j is bigger than 1. And again, this is kind of obvious, because if I have an exchange of two generators, and then I have later on another one, sorry, an exchange of two strings, but in such a way that they don't actually share a string, then I can slide them up and down the braid with no structure. And so in the braid group Bn, non-adjacent generators commute. Of course, adjacent ones don't commute, and that's why this is not an abelian group, right? It is not all elements commute with all other elements. But it's fair to say that most elements commute most other elements. It's only when two braid group elements happen to share a string that they don't commute.
One second. I have a question, then Victor has a question. So you wrote there, hi, sigma I, sigma j is equal to sigma j. What is the other letter?
Sigma j, sigma I. So it's just commutation.
Okay.
Sigma j, sigma I, as long as I minus j is bigger than 1 in absolute value. Yeah, which means that's saying, as long as their distance is more than 1 between the two strings.
Okay. So then Victor has a question.
Sure, go ahead.
Not sure whether this question makes sense or not, but is this representation unique?
Yes. So that's a fair question, right? You might imagine that, I suppose it is unique because what you do is you remove relations if they're redundant, right? So I don't think, no, in a way it's not unique. It depends what you mean by unique, right? Because in a way it's not, because I could rewrite this relationship, right? Sigma 1, sigma 2, sigma 1, sigma 2, sigma 1, sigma 2. I could multiply by sigma 1 inverse on both sides. But that's exactly the same relation. So for finitely generated groups, I'm pretty sure that the representation is unique up to sort of trivial things, right? Up until except for manipulations and the relation. So you can combine relations maybe to give you a new relation, but at the end of the day, it's possible to eliminate some maximum number of relations to have the least possible. Yeah. That's a good question. I'm not completely an expert on this kind of representation theory, so don't quote me on maybe everything I claim, but I'm pretty sure that this is unique, at least in a fairly loose sense.
Okay, you say thanks.
Yeah. Of course. Yeah, so this is often, as I said, this is often called the braid relation, to the point where people often make up groups that are not the braid group, but that might satisfy this 1, 2, 1 is equal to 2, 1, 2 relation. So there's a type of thing called a quantum group, for instance, which has this relation in it. So it's quite a, it's a relation that can make a lot of things happen from the point of view of group theory. So people often just throw in this braid relation as a kind of interesting thing to throw in a group. Okay. So, but again, the real power, right? The real surprise is that this is all you need. That there are no other relations. And that is so it's very easy to show that these are satisfied by just drawing a picture, but it is not at all easy to show that these are the only things that are satisfied. Okay. And the way you do this, by the way, is the way to show that these things are unique is kind of interesting. You do it by acting with the group on something else. And actually, we're going to get into that next. So working with the group itself is often not the best thing to do because the group has these relations that satisfies that are complicated. But if you can get it to act on something like a free group, so let me just say just a quick word about a free group. A free group, which we call Fn, would be like this, right? E1 to En. A free group on n symbols is a group generated by these n generators, but there are no relations, so there's no vertical bar giving some extra properties. The beautiful thing about a free group is if I want to decide whether two elements are equal, so is E1, E2, E1 equal to E2 squared E1, right? Or maybe times E1 inverse. Well, all I have to do is cancel adjacent inverses. And once I've done that, the two words have to be equal, so-called lexicographically, right? They have to be equal from left to right, generator by generator. Otherwise, they're not equal. So equality in a free group is obvious. Equality in a braid group is not obvious. I can write down two long strings of generators, and it takes some work to decide whether they're equal or not. So instead, very often what you do is you act with your group on a free group. And there's a theorem that says that if the action is the same on a free group, then the braids are the same. And so it's actually a far more efficient way of deciding whether two braids are equal than to work on the braids directly. So this piece of software that I've co-written called Braid Lab uses this trick to decide on braid equality. Because there's also algebraic tricks where you try to rewrite the braid into a canonical form. There's a so-called Garside normal form where you try to write the braid in a unique way. And that's very nice, but it's actually much slower than just acting on a free group and seeing what you get. Okay. So I'm mentioning this because free groups will come in very soon, and the action of the braid group on a free group is going to be important. Any other questions before I move on? Check my notes.
No.
Okay. So, why is this important to us? Well, one reason why it's important is because now I can rewrite like interesting Taffy Pullers, for instance, in terms of braids. So one of the Taffy Pullers that we defined a long time ago, or like, a couple of lectures ago, involved rods moving in a concentric circle. So something like this. Is this the right picture? Yes. So there was a Taffy Puller that I showed you a movie of, the one that was, an actual Taffy pulling device, which had a fixed rod, and it had two other moving rods. And these are moving, let me put some arrows here. This one is moving this way, and the other one is moving this way. So there's three rods here, 1, 2, 3. One of them is fixed. That's okay, that's allowed. And when we put a piece of taffy on this, it would grow exponentially. So how do we analyze this? Well, the answer is we plot the trajectory of the three rods in our space-time diagram. So for this particular braid, it looks something like this. for these particular orbits, there's a fixed rod, which is number 3 here. And then the other two move something like this. This is in front and then in the back. And then the other one moves something like this. They move in the back and then in front. I'm asking you to believe me that that's what these orbits look like. It's a bit hard to parse this, right, to analyze directly, but the point is that if you imagine that all these rods are moving, these two rods are moving on circles at the same speed, and then you tilt the picture and draw their orbit in space-time, it'll look something like this. Notice that all the rods return to their initial configuration. So this is actually a pure braid, the definition that I used above. But now I can straighten out this picture and rewrite it as a canonical braid diagram. And in fact, once you do this, using my generators, right? So I would like to rewrite this taffy pulling device as a sequence of these braid group generator sigmas. And I can accomplish this with this picture. Well, notice, for instance, that this is number 2 and number 3. And then after a while, the first thing that happens is that 2 passes over 3. So as far as my braid diagram is concerned, I'm going to draw it like this. I seem to be drawing it the opposite way. Doesn't matter. It doesn't matter, right? It's just a convention which passes over which, as long as you use the same convention. And then meanwhile, the other string does nothing. But then this one passes over this one. And then finally, this one passes over this one. Again, it's a little bit hard maybe to parse this. I think I actually drew the cross. Let me just change my crossings everywhere. It's not going to be a big deal. So you can see again, this crossing is this crossing. Then use a different color. This crossing is this crossing. And then finally, this crossing is this crossing. So I have straightened out the braid to make it look kind of standard. And in fact, I call this braid here, this is sigma 2 inverse. This is sigma 1 squared. Oh, I missed one, I think. Yeah, I missed one, sorry. Yeah, there's another one here, right? There's 4 crossings in this picture. What actually happens is that this crosses twice. Like this. Sorry, there's an extra one. So it's sigma 2 inverse, then sigma 1, and then sigma 1 again, and then sigma 2 inverse. So I would write this taffy pulling device as a braid that maybe I'll call gamma. And I would say that gamma is sigma 2 inverse, sigma 1 squared, sigma 2 inverse. So topologically, I have just captured my taffy pulling device, as a sequence of braid generators. In fact, for this one, I could just take the matrices T1 and T2 that I had in the earlier, at the beginning of the lecture, my 2 Dane twists. And these Dane twists essentially can stand for the sigma 1 and sigma 2s. I can compute the action of the braid on loops in the punctured disc by just replacing the sigmas by these matrices that I had earlier. And so, in fact, if you do this, you will get a, let me just break down the matrix, something like 3, 4, 2, 3. So the matrix 3, 4, 2, 3, which is determinant 1, right? Because it's 9 minus 8, so it's an element of SL2. And if you compute the largest eigenvalue of this matrix, which will give you growth of this taffy puller, then you will find that the largest eigenvalue is sorry, I'm messing up my notes. 3 plus 2 root 2. So the dilatation lambda is equal to 3 plus 2 square root of 2 for this particular matrix, which actually can be written as 1 plus root 2 all squared, right? Because 1 plus root 2 squared is 3, and then there's a cross term, which is 2 root 2. And the reason why this is neat is that 1 plus root 2 is a kind of a special number that I denote often by chi, the Greek letter chi. Chi is called the silver ratio, and it's a far less well-known number than the golden ratio, but it shows up in Taffy Pullers all the time. It has a continued fraction representation of 2, 2, 2, 2, 2, 2, 2, whereas the golden ratio has a continued fraction representation of 1, 1, 1, 1, 1, 1. So it's the next natural, noble number following the golden ratio. In fact, there's the bronze ratio, which is 3, 3, 3, 3. After that, they're called the metallic means, but you can define them. It's just a definition. So this is larger than the golden ratio, and so it tells you that this device kind of pulls a bit faster than if it just had the golden ratio squared as its denotation, which was the Arnold cat map case.
1 second, there is a question.
Of course.
Would you mind to explain how to get to the matrix form of the quantity gamma again, please?
To get to what, sorry?
How you get to the matrix representation? How you
to the matrix representation?
Yeah,
okay. Yeah. Let me say that in more detail. So, if you remember, draw a big picture. When we had a disk at the beginning of the lecture, I drew a little loop around these two rods, and I told you that if I acted with T1, that this mapped this loop to this. Okay, so in other words, if this loop is called, let's call it alpha, then the yellow loop is T1 times alpha, where T1 was the matrix that I had earlier. Okay, and the way I'm claiming this is that I take T1 as a matrix, I take this loop on the torus, and where we know how to represent loop by two numbers, and I act with the matrix on the loop, and then I project back down to the disk. Okay, and so that tells me the image of alpha is this kind of loop. Now observe that this is exactly what you would have gotten if you started with this loop and you did a clockwise interchange of the first and second puncture. Okay, so that is important. So thank you for asking the question, right? How do I get from this white loop here around rod 2 and 3 to a stretched loop around rods 1 and 3? And that's by interchanging clockwise rods 1 and 2 and dragging the loop along. And then the image of the loop will then be something like this, topologically. So that's why I can identify T1, because I know that the exchange of the first two rods is exactly what I define as the generator sigma 1 of the braid group. I can identify the action of sigma 1 on the disk by using the matrix T1 on the torus. So here what I'm doing is I'm using sigma 1, and I don't remember if sigma 1 was I think sigma 1 was 1, 0, 1, 1, right? And then sigma 2 inverse was 1, 0, 1. I'm squaring this one. So I'm just carrying out this matrix multiplication for sigma 1 and sigma 2, and I'm getting to this. And it makes sense as a taffy pulling process, right? Because what it's saying is that as I act with these matrices on these loops, the loops are getting more and more entangled onto these punctures, and it's exactly the rate of this entanglement that I'm trying to calculate. Does that clarify the situation?
Yes, he said thank you. I
Okay.
see now.
Okay, great. Okay, no, it's a very good question. So in a way, we're still lucky, by the way, because we can still use linear algebra to do this. Right? In the sense that I've shown you now an example with 3 punctures, but it turns out that linear algebra goes out the window as soon as you have 4 or more punctures. It's not possible to just compute everything you want by just manipulating matrices. In other words, the torus is very special, right? And if you go to disk with more puncture, there is no kind of mapping of the torus to these punctured surfaces that gives you these nice linear representations of pi1. So we're going to have to work harder to compute the growth on things involving more punctures. Okay. So how are we going to do that? Well, we're going to do it a little bit indirectly, like I mentioned, by looking at the action of the braid group on something else, on a free group. So last chance to ask questions about this Taffy puller before I clean up a bit. Okay. So recall what we had at the very first lecture, which was the fundamental group of the disk. So this is a disk. This is a few points on the disk. I'm going to draw 3 punctures, but really I have in mind n punctures. And remember that the elements of the fundamental group are loops. They're oriented loops based at some point x0, which we often pick to be on the boundary of the disk just for convenience. And these loops we denoted by E1, E2, and E3. And pi1 contains equivalence classes of these kinds of loops. But you can kind of see that it's impossible to drag E1 onto E2 because the puncture itself acts as an obstacle. That's the point. And you can imagine if I wind the loop around the punctures, then it'll live in its own equivalence class again. So for that reason, E1, E2, E3 form a free group. So in fact, we would say that pi1 of the disk being free is isomorphic to F3, the free group on 3 symbols. Not so on the torus, right? The pi1 of the torus was an abelian group, but for disks with punctures, the fundamental group of loops is very simple. It's just pi1. It's just a free group. You can see that if you add more punctures, that's not going to change, right? You can't commute these two distinctions. Okay. So what we would like to define now is an action of the braid group onto pi1 of D3. Okay, so an action, we'll write it as sigma I star. So in other words, given a generator sigma I would like to compute some mapping from F3 to F3. From the free group on 3 symbols to the free group on 3 symbols. Okay. So how am I going to do that? I'll say a bit more about what an action is, but an action is exactly what it sounds like, right? It's a map, but the important thing is it's a group homomorphism, meaning that the action itself respects the group properties. So in other words, if I were to do sigma I star followed by sigma I star inverse, that would have to be the identity map on F. Okay, so an action is a mapping of, each generator of the group induces a map from F3 to F3, but in a way that it respects the group operations and the presentations and everything. So in fact, it is a representation of the group, right, in terms of maps from F3 to F3. Okay. So how do we define this? Well, again, this field is very visual. So what we're going to do is we're going to draw a picture of what happens if I switch. So sigma 1, if you remember, is the clockwise interchange of 2 of my punctures. So what if I do a sigma 1 operation and I drag along the loops as I go? What would be the image of acting with sigma 1? Okay. Well, let's see. if you think about it, this E1 loop will wrap around now because the puncture E1 will move here and the loop E2 will have to move under. So in fact, the picture will look like this. And then E3 will be left alone. So what am I drawing here? This is the image of E1. Because E1, again, I move my puncture such that E2 goes underneath and E1 goes above, so the loop gets dragged along and passes above the original E2. So this is the image of E2, and this is the image of E3 under the map sigma 1 star. So let me just write sigma 1 star just for concreteness. So I can write that sigma 1 star. Sorry, let me find my place in my notes. Actually, let's think about what this is as an element. What is E1 prime as an element of the fundamental group? Right. So let me just draw it by itself. So E1 prime kind of looks like this. Of course, that's not really anything in particular, right? So I have to be a little careful. I kind of have to do it in such a way that I can write it as a composition of loops. Sorry, I have to draw my other puncture here. There's a puncture here, but notice that this puncture is kind of on the, like it's on the outside, it's in the wrong place. So what I want to do is drag this down to create a kind of E1 here, right? To create image of an E1. So I'm going to drag this down and this down. And then I'm going to rebound and go here. So all I've done is I've pinched this part and I've kind of dragged it down to X0. And now you can kind of see the trace of my loops a bit better, right? So my image E1 prime, I need to draw an arrow. So E1 prime, I follow my arrow. I'm going to draw an E1. Then notice I'm going to be going around E1 again, and then an E2. Sorry. This point here is looping around puncture number 2. So it's E2. But then I'm down here and I need to wind back around puncture E1, but the wrong way. So that's an inverse. So I have that the image of E1, when expressed in terms of the elements of the fundamental group itself, is E1, E2, E1 inverse. Okay. That's a little bit hard to wrap your head around if you're not used to these kinds of calculations, but maybe you can kind of see that. Again, in order to carry out this pinch down to bring it back to the base point, so you can write it down as a sequence of loops, you kind of have to go around E1, then around E2, but then back around E1, right? You kind of have to undo what you just did. Okay. And because this is not an abelian group, this is a free group, there's no way to commute these, right? So this element is just E1, E2, E1 inverse. Okay. So we're almost there because we still have to find the image of E2, but that's easy. E2 prime just became E1. Right? Not much happened to E2 prime. So just list those here. So E2 prime is E1. And then finally, E3 prime is E3. Okay. So that is, notice that this is a map from F3 to F3, because if I give you E1, E2, E3, their image is these elements of the free group. And so therefore this defines sigma 1 star. Okay. So this is a mapping of a free group to itself. So for instance, and I worked it out by acting on one generator. But let's say I had sigma 1 star acting on E1, E2. Okay, then this would be sigma 1 star of E1, sigma 1 star of E2. In other words, you have to kind of act on every generator as you go. Okay. In order to satisfy this group homomorphism property. And so then there's a similar relationship for sigma 2 star in this case. If it's a disk with 3 punctures, then there's nothing else, right? Meaning there's only sigma 1 star and sigma 2 star. But in general, I think you can kind of see that much like everything involved always a sequence of 3 strings, and I could ignore the other strings, the same thing happens for the case of the general braid group, and that I can rewrite this, replace this by I plus 1, and I can write E1 plus 1 prime, sorry, EI plus 1 prime is EI, and EI, everything else is left alone. So the action of sigma I star is just to map EI to EI plus 1, EI inverse, and to map EI plus 1 to EI. And every other generator is untouched. It just maps to itself. Now, you can prove easily that this now satisfies all of the group relations. Meaning, for instance, sigma 1 star, sigma 2 star, sigma 1 star, acting on any free group element is equal to sigma 2 star, sigma 1 star, sigma 2 star, acting on the same free group element. So in other words, this is why this action on the free group is actually a representation of the braid group, because it satisfies the actual presentation, all the relations in the braid group. And again, it takes a little bit of work. You can do this algebraically, for instance. It's totally fine to do this using algebra to prove that that you can do this. You can also do it kind of visually if you want, but it's fairly easy to convince yourself that this is the case. And same thing for commutation, right? What happens with commutation is that if things are far enough apart, then two things are unrelated, and then it's obvious why it works. Okay. So this would be, for instance, one way to decide on braid equality, because this thing is an element of a free group, and this thing is an element of a free group. So two elements of a free group are the same if and only if you can read them from left to right in the same way. So actually, this action on the free group can be used to determine whether two braids are equal, because if I write them down in a funny way and not sure that they're the same, I just act on an element of the free group, and if they give me the same thing, then they have to be the same braid. Okay. It's a so-called faithful representation of the braid group. But this is not actually great. Like, it sounds like a magic way of determining equality, but it has a big flaw. The big flaw is that the action is hard to compute. Right? If I can just consider my braid sigma 2 inverse, sigma 1 squared, sigma 2 inverse. This is the braid that we just wrote down corresponding to the Taffy Puller. And let's say I consider the star of this, so the action on the free group acting on, say, the generator E1. Okay? So I can do this, okay, and I'll get some sequence, right? I won't do it because even that is a little work, but I'll get some E's here, right? Some product of generators. But now let's say I want to do it again, right? let's say I want to act on this thing again. Now I have to act on each of these generators individually, and each one of these will satisfy this kind of relation. Okay. So if you keep doing this, repeatedly, if you do this repeatedly, if you keep acting with the group, with the braid onto the same group element, free group element, the number of symbols, the so-called word length, the reduced word length, once you do some cancellation, will actually grow exponentially for the braid that we discussed. We know that it grows exponentially because these loops, they're like pieces of taffy as well, right? If I had designed my taffy puller where I anchored a piece of taffy around a rod, but I anchored it somehow onto the taffy device, you can see that doesn't change anything, right? The piece of taffy is still going to stretch, fold and grow exponentially. So the number of elements here is exactly a measure of the length of my taffy. There may be a little bit of redundancy, right, because of the fact that I'm anchoring the thing at this point, but roughly speaking, the number of symbols that I see here is exactly a measure of the length of my piece of taffy that's being wound around my taffy pull. And this is bad news because it means that if I act with this repeatedly, the number of symbols here will grow exponentially at a rate. So if I take the power k here, for large k, this will go as silver ratio to the 2k. Because remember, the largest eigenvalue of our matrix was chi squared. So power k, it'll go roughly at the rate chi to the k. Well, in fact, it'll grow exactly at the rate chi to the 2k as k goes to infinity. But since chi is about equal to 2.4, in fact, the silver ratio, 2.4 squared is 5. So this is 5 to the k, roughly speaking. And 5 to the k grows really fast, right? 5, 25, 125, 725, 625. And so you will rapidly, you cannot even implement this on a computer, it turns out. Let's say you wanted to compute the growth by acting repeatedly on the same word. It is actually not, many people have said, oh, this should be an easy way of computing the growth rate of a taffy puller. I'm just going to implement this kind of symbolic dynamics in Mathematica and just, plot the number of symbols, right, as a function of the power k here on a log plot. And I should get a straight line. And the slope of that straight line is the growth rate of my taffy puller. That sounds like a reasonable thing to do until you realize that even after like 10 iterations or 20 iterations, you've run out of computer memory. Right? On any modern computer, it only takes a handful of iterations for the thing to run out of memory because it's an exponential process. You might be able to get a good fit for your line in 10, 20 iterations. So it doesn't actually, it's not bound to fail, but for some braids, it's actually quite difficult to do. It's not a very bulletproof method for computing the growth, even numerically. So this is the moral of the story that I told you in the last lecture, or at the first lecture, I told you that pi1, the fundamental group, often has to be abelianized because we kind of hate free groups in some way. Because free groups, they just, you have to count every single symbol, right? If you have 10 symbols, you have to write them 10 times. You can't write it as 10 times the symbol. You have to write it out 10 times because nothing commutes. So there is no linear algebra in a free group. And so life is difficult. And you have to do the symbolic dynamics, etc. So I told you that often it was better to pass to what's called the homology group, which is where you just assume that everything commutes. Okay. Well, okay, so let's think of what would happen if we define our action on H1 instead. And H1 is the homology group of the disk. So it's exactly the same group as pi1, except that all the symbols commute. Well, you go back to your relation here, and you write this additively as EI plus 1 minus EI. So in fact, if you abelianize, you lose this conjugacy. You lose the fact that the image of EI is EI plus 1, EI minus 1, because these things commute. The first term and its inverse now cancel, and you have that the image of EI is EI plus 1, and the image of EI plus 1 is EI. Perhaps you recognize the action of this group. This is the so-called symmetric group, because all I'm doing is I'm commuting the elements. So the abelianization of the action on pi 1 actually gives me the symmetric group, not the braid group. The braid group is a representation, sorry, the symmetric group is a representation of the braid group. It's just a bad one, okay? Because there's a lot of extra relations, like commutativity. And you might imagine that in the symmetric group, nothing is going to grow exponentially. I'm just switching the positions of these loops around, but nothing is happening. So the process of abelianization lost too much. On the one hand, I have this action on the fundamental group, which is perfectly faithful to the braid group, but it's too difficult to compute with. And on the other hand, I have this totally commutative version of the action, and that one just gives me the symmetric group or the permutation group. And that's a boring group, right? In the sense that it doesn't do very much, and it's never going to detect the growth of our Taffy in any meaningful sense. So the question is there a way to do something in between? Is there a way to have our cake and eat it too, right? Is there a way to use linear algebra to still capture some of the growth without throwing it all away by going to the symmetric group? And that's what I'll discuss in the next lecture, is how do we turn this into a better representation of the braid group, in fact, a linear representation of the braid group, but that is not as trivial as the symmetric group. So I'll pick up on that in the next final lecture, 1 week from today. All right, thanks.
Thank you. It was wonderful. Wow. Very, very nice. So let's thank Jean-Luc for this wonderful lecture. Please join me.
Thank you.
So any other question? 1 second, I have to. 1 second, I'm looking. Victor. 1 second, I'm looking here. There was some question on YouTube. Sometimes it's hard to watch two sides.
Yeah, there's many things to keep track of.
So Brian is joining us here to ask you directly on Zoom. So please, Brian, you had a question. Brian? Brian Maurice?
Hi.
Hi.
Hi. Yes, that was in YouTube, but okay. Thank you, Professor, for the lecture. I was wondering if you have, if you do the way inverse. I mean, if you had a complicated list of symbols, can you demix the process, the state? I mean, can you return in the action to get the unmissed initial state?
Yes, everything here is invertible. Absolutely. Yeah, there is no mixing in the sense of, everything is deterministic. Remember, this action is just it has to preserve the actions of the operations of the group, and so it has to respect the inverse as well, right? So yeah, I think that's right, right? Yeah. Well, no, wait a second. The representation could send everything to the identity. Sorry, maybe it depends what you're asking, right? But if you mean as far as the thing that it's acting on, then yes, it should return, right? But you can, for instance, imagine mapping everything to the identity, right? That's the least faithful representation you can do, is you take every group element and you map it to the identity element of whatever space you're acting on. So for instance, I could say that any sequence of braids is the identity, right? But I mean, it's still invertible, right? Because if I'm acting on E1, I mean, I still know how to go back to E1, right? Because that's just the identity map. So the thing you're acting on here is always invertible. You can always go back, basically. But it might not tell you much depending on how faithful your representation is. Yeah. But yeah, there's always a way to go back. You're not really mixing here and losing information. Does that make sense? Sure.
Yeah, that makes sense. I was thinking in a fluid. I have seen that experiment that you steering it that way, and by reversing the steering, you came to the initial position of the fluids. Yeah. So I was thinking in that.
I mean, that is related in the sense that this is the famous fact that in Stokes flow. This is not true in general fluids, right? So should be careful. It's not necessarily. So if the fluid is very viscous, then the motion of the rods determines uniquely the state of the fluid, right? And therefore, if I reverse the motion of the rods, everything goes back to where it was. That's the context of exact diffeomorphisms, if you will. But in actual fluid, if you move the rods faster, you start shedding eddies. So that if you go back, your eddies are still going. You're not undoing the vortices that you created. Right? So this idea that the fluid goes back to where it started only works for very, very viscous fluids. Otherwise, the theory that we're doing here is still correct, but you're only going back to where you started in an isotopic sense, in the sense that you're only deformable to the same initial conditions, but your actual map might involve lots of complicated structure, right? But it can all be smoothed out to give the identity map set. Okay, so this is by no means an exact representation of fluids. Right? It's a kind of cartoon, and it works best in this viscous limit. If you think of very turbulent liquids and things like that, this kind of descriptions by diffeomorphisms, by equivalence classes of diffeomorphisms, it loses a lot of information about what's actually going on in the fluid. But that's a good question.
Thank you.
We have another question from Victor. Going back to the gamma element again, its eigenvalue psi represents the growth rate of the string. What about its eigenvectors? Do they have a clear physical meaning too?
No, unfortunately, the second vector is far less well-defined in terms of, in some sense, mathematically. So what we're hitting on here is so-called parallel Frobenius theory, right? So these are matrices that are non-negative matrices. Actually, no, there's a way to map this theory onto non-negative matrices by sort of inflating the space a little bit. And there's something very special about the leading eigenvalue in parallel Frobenius theory, and that's it's associated with a positive definite or non-negative definite eigenvector. So in this theory, the leading eigenvalue is special because it has an invariant density associated with it. There's a positive eigenvector that you can build out of this, which kind of tells you how the pieces of the taffy are mapped together. So the invariant density, if I have my piece of taffy here, right, it winds a certain way, but it might wind a bit more on one side than on the other overall. That's what's called the invariant, the asymptotic invariant density. In this case, called an invariant foliation of the map, of the equivalence class of the map. And that is tightly associated with the leading eigenvector. The other eigenvectors don't have guarantees of being positive. So they're distributions, they're not densities. Phil Boylan, I believe, has written about this. So there are some interpretations of what happens with the second eigenvalue. In particular, it might determine some convergence rate to certain things, but I don't have a good physical intuition as to what the second eigenvalue is useful for. I don't know if that helps answer your question, but it's, yeah, I think the second eigenvalue is a tricky object in some sense, and I'm not sure exactly what to do with it.
Yeah, so I think yeah, will be good to see how the eigenvalues and the eigenvector have this meaning. You know, I think his question was about what about the associate eigenvector to to this.
Yeah. Yeah.
Yeah.
Yeah, so if you remember, the eigenvector on the torus was actually associated with this winding process, right? Because it was the irrationality of the eigenvector on the torus, which when you map it down, so on the torus, it means that this curve never closes. But when you map it down to the disk, it gives me exactly this kind of complicated winding pattern of the Taffy, right? And the entries of the eigenvector are related to the mass, the relative mass that you get in the different parts.
Okay. He says, that's cool. Thank you, Professor.
Yeah, it's neat. I don't think people have used that very much. The invariant density has not been like exploited for any kind of purposes in experiments or things like that. It's not, I mean, in this context, right? Invariant densities, of course, appear everywhere in physics and mathematics, but as far as applications of this, I'm not aware of people actually using this for some optimization purpose.
So that's great. So actually, you send us the notes. If you have some extended version, more, really appreciate. I know they have a lecture, no, on braids.
There's no lecture on there on braids? No, I guess not. Maybe these are kind of older notes. I'll look for something. Yeah.
Yeah, you don't have any course that you gave online on braids, no? Online course on braids.
I do. I have these handwritten notes on braids. I also have, unfortunately, the book that I just finished.
Ah.
I'm not sure if Springer would want me to start giving it away yet. But it's going to come out this summer. So that has this stuff in it. Maybe I could circulate just a chapter on braids or something. I think that'd be fine.
Thank you.
Yeah.
Really appreciate it.
But yeah, there's going to be a nice little book. It's going to be a short little book called Braids and Dynamics coming out this summer.
Ah, that's great.
I think it'll be a cute book. It's like a book with 150 pages, but like 80 figures. So maybe 100 figures. So it's mostly pictures. So it's good.
I'm sure it will be wonderful. Okay. So thank you once more, Jean-Luc.
Thank you. See you next week.
And see you next week. We are very much looking forward to see how you solve the mystery now.
Yeah.
Thank you. Yeah. Thank you very much. Thank you.
Thanks.
Bye-bye. Bye-bye.